Today we're going to discuss potential flow, what it is, why it's really useful. But before jumping in, excuse me, just wanted to make one remark from the last lecture. If you watched about far field forces, remember how we went through some gymnastics to kind of create this weird control volume that went around the body. We never have to do that again, because remember the upshot was that the cut sections always canceled out, and the integral around the body, all it reduced to was the force that the body produced. So we could just create our regular control volume, and anytime there's a body in there that's not fluid, that's fine. We just remember that what we need to do then is to add the force that the body, or we add the term, right, that the force that the body produces on the fluid, right? So we're just kind of jump directly to that. Okay, so potential flow, let's discuss what this is. The first step, or the assumption really of all potential flow, is that the flow is irrotational. Okay, so what does that mean? Well, mathematically, it means that the curl of the velocity field is zero. And you may recall that the curl of the velocity is the vorticity. You may also recall that vorticity is twice the rotation speed. So that means that if I was looking at little control volumes of fluid, that they are not rotating. And it's irrotational. Okay, so this is irrotational. A prerequisite of being irrotational means the fluid must be inviscid, because any viscous fluid is rotational. You could think of it that if I've got this wall of fluid, a uniform flow coming in, and there's say a wall, and I pass by that, well, the velocity, the flow, the fluid particles close to the water are going to slow down. Those on top are going to speed up, right? It's kind of like a pile of books, and so these fluid particles are rotating, right? Because it's going faster on. If I took a control volume, it's going faster on top than the bottom, so it's going to induce that rotation. The opposite is not necessarily true. Just being inviscid is not necessarily enough. But if I'm inviscid and I start irrotational, I will remain irrotational. So the most common scenario there is that I've got a inviscid flow, and I start with, say, uniform inflow. If I start with uniform inflow, I'm going to have streamlines that come around, but as long as I don't introduce viscosity, this will be an irrotational flow. Well, why is that useful? Well, it's not by itself super useful yet. There is one usefulness, and show this, that there's a vector identity that the curl of any gradient field is always zero, where phi is just some arbitrary scalar function, anything. This is always true. The curl of any gradient field is zero. If we compare these two, we could say, well, then I could, if I have irrotational flow, I could always represent my velocity field as the gradient of some scalar function. One convenience there is that I've reduced this three-dimensional flow field to a one-dimensional function that I could solve for. And once I solve that one-dimensional function, I just take its derivatives and recover the three-dimensional flow field. And that's where the full potential equations come. If you remember, a few lectures ago, we made this chart of things and just mentioned the full potential equations in passing. That's what this is. We have the Euler equations, and everywhere we have velocity, we replace it with this. And the idea is that, well, now we have one-dimensional functions. Conceptually, that's easier, but in practice, it's still pretty hard to solve. So it's not really that much better. However, if we make one more assumption, then we're going to get a big benefit. So we're going to keep a fluid as irrotational, but if we also assume that it's incompressible, then things start becoming really nice for us. If you remember mathematically, the condition for incompressibility is this, that the divergence is zero. That's the incompressibility condition. So if something is incompressible and irrotational, right, here's the irrotational condition, we plug that in, get the divergence of this gradient field is zero, or in other words, we get Laplace's equation. Laplace's equation, okay? That's big for several reasons. One is, imagine what we've done here. We've taken the Navier-Stokes equations, which are unsteady. There are four equations. They're nonlinear partial differential equations that are coupled. And by making these two assumptions, we've reduced it down to this one equation that's simple, right? And it's a linear PDE. If I was writing Cartesian coordinates, it would just look like this. And that's it. That's the whole governing equation. But even better is that this is a linear PDE. And a linear PDE, if you remember, means I can use superposition. So if I have solution A and solution B, then A plus B is also a solution, or 3 times A plus 5 times B is a solution, any linear combination. And because Laplace's equation is, this is a well-known problem, we know lots of solutions. In fact, we know some very fundamental elementary solutions that we'll discuss today that we can combine to create sort of any incompressible and irrotational flow field that we want. So this is kind of why this is a big deal. So let's ask ourselves then, well, we made some assumptions. How useful are those? Well, it depends. There are actually a lot of scenarios where this can be quite useful. So for example, say I have this airfoil and I want to, and here I'm just going to draw some streamlines. So it looks like this, right? The flow around this airfoil. And if I was to inquire around here in the flow field, where is this irrotational? Where is this incompressible? Well, it turns out that it's going to be irrotational pretty much everywhere. The only places where that would be a bad assumption is, of course, where viscous effects are strong. And that's going to be in this very tiny region, as long as, we're not separating, in this very tiny region in the boundary layer and in this, perhaps in this small wake. But basically everywhere else, this is a very good approximation. What about incompressible? Well, as we recall, that's a good assumption if we're at low Mach numbers, say under Mach 0.3. So for low speed aerodynamics, this is great, right? And this is also widely used in hydrodynamics because fluids are essentially incompressible, or liquids, I should say, water. So for low speed aerodynamics, this is a big deal because we have these equations that are way, way easier. We have known solutions, we can combine them very, very fast, and they're good for a lot of applications. Now, if I've got blunt bodies, like I'm doing my horrible rendition of a car, or let's just not do a car because I'm so bad at the car. Let's do the airfoil where I've got big separation now, right? It's at a big angle of attack. And now, it's got this big wake. Well, now this is not so good, right? I can't use potential flow anymore. Or if I go to high speeds, right? I can't do that. We'll find, though, that later in the semester that we can actually push this a little bit, and we can use potential flow at higher Mach numbers, still subsonic, and even some supersonic Mach numbers, just not near Mach 1, with some corrections. In fact, we can get a little bit near Mach 1 if we assume small disturbances. So there are some things we can do to even extend the usefulness of these methods. So what is phi? Well, it doesn't really have a physical meaning. It's just a potential function. One way, if it helps, if you want to visualize it, this is just showing streamlines in black around the cylinder. And again, there's a potential flow, so you can see that it's symmetric. There's no wake. These white lines are lines of constant potential, and they're just everywhere orthogonal to the streamline. So if that helps you to visualize, that's fine, but that's not too important. One other preliminary we need to cover is just circulation. Recall, we already talked about vorticity a couple times now, right? It's the curl of the velocity. Circulation is related to that. Circulation is, this is how we normally define it. We define it as the line integral over some contour. Right, so if I took this contour and I integrate around, I go around this contour, and sorry, I wrote gamma when I meant V. I evaluate the velocity and I get the component along my contour and I just integrate around it. It gives me my circulation. And by Stokes' theorem, which we saw before, this is directly related to my vorticity. This is my vorticity that crosses that boundary. Okay, so they're related, but the circulation tells me something about lift. So the circulation in this contour is 0, whereas the circulation that goes around this airfoil is directly proportional to the lift. At the end, we'll see exactly how it is. So anything that is not encompassing that lift It's going to give me 0. It has no vorticity. It's irrotational, right? So it's irrotational everywhere. In other words, my circulation is 0 everywhere, except for because this is a real airfoil, it has real viscosity. If I include right around it, if I include it in my control volume, there is vorticity, some net vorticity generated, and that's going to create a circulation. All right, so we mentioned Laplace's equation has some known solutions. Let's talk about some of them, the fundamental ones. So first, 0th order, just uniform flow. Here we're showing at an angle of attack. You can ignore this line here. I'll just say briefly, passing if you're interested, you can look in the book. We can actually form Laplace's equation for the stream function, and that's perhaps more intuitive physically, but it only works in 2 dimensions, so it's not as generally useful, so we won't use that. This is the potential function, and then remember to get the velocity components, that's actually all we need to know. Just go back to the definition, right? V is the gradient of phi, so in other words, Vx is d phi dx, and Vy is d phi dy, for example, all right? So we can see that occurs. So that's one. All right, so one of our first order solutions is what's called a source, or it's called a sink, depending on the direction. And again, I'm going to cross this out. This is our potential function. Notice I'm writing it in cylindrical coordinates as a function of r, where r is the distance I am away from the center of this source. Okay. Lambda here, capital lambda here, is just a constant. It's something I get to choose, just like v here is a constant I get to choose. I can make my velocity bigger or smaller. Lambda does the same thing. It makes this stronger or weaker, right? It kind of changes the velocity directly. And notice if I take, I'm going to do the gradient in cylindrical coordinates this time instead of just x and y, but we can do an x and y. Sometimes that's more convenient. But for this case, we notice that what the source or sink does is it creates only radial flow, no tangential, so everything just comes out radially. Notice that it becomes very strong as I go to the center. In fact, it's undefined at the center, it's infinite, so there's a singularity at the center. And as I go far away, as r becomes really big, this drops away to 0. So as I get far away from my source, there's no influence. As I get really close, it's really big. Okay, so the other elementary solution, first order elementary solution, is a vortex. It's the opposite in some sense, the opposite in the sense that it produces no radial flow, everything is tangential. So all the velocities go around in these circles here. It's a little bit hard to see from this rendering, but these would be perfect circles, right, that it comes around, okay? I think of it like a hurricane or a bathtub drain or whatever. Again, we'll cross this one out. Here's the potential function. Gamma is again, the arbitrary constant we could choose that changes the strength. It's our vortex strength. It also happens to be the circulation. Well, not happens to be, that's why we use gamma. So if I take an integral that goes around that singularity, I will get gamma, any integral around there, the outside of that circulation is 0. And this is the tangential velocity. Again, similarly, as I approach the core, it approaches infinity. This is called an ideal vortex. A real vortex, you know, viscosity plays a role eventually, and the velocity gradients are so big, right, that viscosity would be important. So, right, obviously the velocity at the center of a hurricane is not 0 because there's viscous effects, but for an ideal vortex, it keeps going all up to infinity. And just like the source, as I go really far away, this dies off towards 0. Okay, those are the first order ones, and I can create any incompressible rotational flow field with just those solutions. I can superimpose them. Remember I said we could superimpose them. If I put them in the right places, the right strength, I can create any sort of flow field I want. But there's one more that's useful, especially in 3-dimensional aerodynamics. We won't use it as much in this class, but it's called a doublet. And conceptually what it is it's, you take a source and a sink, you put them infinitely close together, and their strengths go to infinity as well, but the product of those two stays finite, which maybe is a weird thing to say, but it looks kind of like this. It's directed from the source towards the sink, and then, you know, these are kind of curling out from the source back towards the sink again. Okay, if I didn't say it, the sink is just the source where gamma is negative, so everything's coming in instead of going out. And of course, the vortex, we could change the sign so things spin the other way. Same with the doublet, we could flip everything over. Okay, so the doublet, again, like I said, we won't use it as much in this class, but it's widely used in three-dimensional aerodynamics. It's a second order solution to Laplace's equation, if you will. All right, so let's just give some examples of why this might be useful. Let's say I take a uniform flow. Actually, let me just skip over to this blank page here. Let's say I've got a source, and the source looks like this. Okay, and then I'm also going to put a sink here. It's going to be a little bit ways away. And then well, actually, let me just start with that. Let's just start with the source, and I'm going to add a uniform inflow. And remember, we said we can superimpose these. So, and that will also be a solution. So the source, I'm just going to remain fixed. The uniform flow is going to go everywhere. So if we were to draw these streamlines, we could think that perhaps they kind of come around. The source is going to kind of push it around. It's going to kind of go like that. And indeed, it will do something like that. But let's think about what happens right here on the center line, right? If I drew a line that goes right to the center of this source. Well, this velocity is constant, but this source velocity is not, right? The source velocity looks like this, radially outward. Gamma is some constant I choose. It's gamma over 2 pi r. Notice that, again, towards the center, it's infinitely large, and far away, it goes to 0. So I have every velocity possible. So I know that somewhere along this line, this arrow is going to exactly cancel with that arrow, right? And that's going to be my stagnation point. So there's some stagnation point somewhere where this V, right, which is going this way, is exactly the same as lambda over 2 pi r. In fact, I can find out exactly where that is. That's just when these things are equal. So that occurs when r is equal to gamma over 2 pi v. So I can adjust those strengths. I can choose gamma, make my source stronger or weaker. I can change v and make this free stream stronger or weaker. But they're going to create a stagnation point that is exactly r away from the center of that, that source. Okay, and there's some streamline, and that's a stagnation point, right? The velocity is 0 there. There's some streamline then that passes through that stagnation streamline. It looks something like this. It's going to go shape like this, right? So everything on this side is going to be slowing down as I approach that, because this velocity is now bigger than this one because it's decaying. So I'll get, and it'll slow down until I get to that stagnation, and then everything else is going around like this. Okay, so I get this kind of shape, and there's other streamlines that come around and so on. If I also, this will kind of continue on like this, but if I also create a sink so that this is symmetric, I make it the same strength. What will happen is the exact same thing will happen, only opposite. It'll pull this back in. I'll get another stagnation line like this, and my streamlines will come around like this. It'll look exactly the same on the back, just opposite. And it'll look like this. It's called the Rankine oval. The upshot is this, though. If I had replaced this oval with a solid body, an inviscid solid body that was this exact same shape, and I just stuck it in, then I get the flow field that occurs around the shape, because this is this dividing streamline gives me the stagnation point, and it gives me the no inflow streamline around that body. So in other words, I can now compute the velocity everywhere around this oval shape. I can get the pressure and so on. I can figure out the forces. I can get my entire flow field just by superimposing, a couple singularities that have these analytic formulas that I can very easily calculate the flow field anywhere I want. Okay. Just to give you another example, actually, I'm not going to show it in interest of time, but you can go look in the book, or every aerodynamics book will have this as a cylinder. I take a uniform flow in a doublet, that creates a cylinder. In fact, that shouldn't be surprising by what we said a doublet is kind of taking the source and sink and moving them together. So let's just talk briefly about some real life applications of some of these singularities. Vortices, for sure, you've probably seen a lot. If you haven't, I'm not going to show these videos here, but I encourage you to go search for some of these videos online. Go look at the vortex behind an airplane. And you can see it with real life airplanes, you can see it with paper airplanes, you can see it with anything that creates lift. What happens is as the airplane flies through, so here's the back view of my airplane, right? And as I fly through, I get this pair of counter rotating vortices, or in the side view here, here's my airplane, right? Something like this. And I get these vortices that trail off, right? Like this. So if I was to take a cross-sectional view here, it would look like this. And what happens is that based on the rules we just saw, these vortices, this induces a tangential velocity. So this vortex induces a velocity on this one downward, and this velocity induces a velocity on this one also downward. So they push each other down, and so the whole wake descends. And that should make sense from a momentum conservation, that if my airplane is lifting, that means the fluid is pushing the airplane up. So conversely, the airplane must push the fluid down. This also helps to explain formation of flight, that remember that these vortices are creating velocities that are, going tangentially like this. So over here, it's downward. But if I'm another bird or airplane, right, and I'm kind of over here, which means I'm in this space over here, you can see I'm in an area of rising air. So if I can get behind and to the side of another bird or a plane in kind of this formation, and typically you'll see this kind of V formation, then I can get in a region of rising air from those vortices. I can get some free lift, if you will, and reduce my lift-dependent drag. There are also a lot of applications of ring vortices that you might see. That's another cool video to go see. There's a lot of them on the internet about ring vortices. It's kind of the same concept here, right? If I have this cross section, in this case, we have a line, right? So if I took this dot here and I extended in a line coming out of the board, that gives me this shape here. But instead of creating a line coming out of the board, imagine I create a donut. So I take this one and I pull it out into a circle coming out of the board and I go back in. So there's kind of this donut that goes out of the board and then it goes into the board. Right? I create this donut shape. I can't quite draw that, but imagine I take that ring vortex. Then and the same thing happens, right, where this right one pushes the left one down, the left one pushes the right one down, but that occurs for every pair along this donut. So the whole thing, if I could just create this ring vortex and sit it here, it'll just self-propel, it'll move this kind of smoke ring. And a lot of cool videos about that. And in fact, other cool stuff will happen if I take one ring vortex and another one right next to each other, they'll leapfrog. The one will kind of get bigger, the other one will go through it, and then the other one will get bigger and go through it, and they'll kind of leapfrog each other. And you can see actually this kind of behavior happen in the wake of like a propeller or a helicopter sometimes. And so anyway, lots of cool things you can go look at with vortices. One other sort of application to help you where these could be useful is in what's called ground effect. Remember, we could use these singularities to represent these bodies. And in this case, I want to represent a body that's just a flat line. I want to represent the ground. So here's, say, a wing, right? It produces these counter-rotating vortices. And if I want to represent this ground, one way I can do it is I can mirror those vortices over. So if I mirror them over, then we can see that this is actually going to produce a ground plane. So imagine I compute the velocity at this point. Well, this vortex induces a velocity. It's always going to be at a right angle, right? It's tangential. So at a right angle there, and based on the way that's curling, it's going to induce a velocity that way. Whereas this vortex here is going to induce a velocity that way. So the up and down components will always cancel and I just get a sideways velocity. So this will occur at every point along here. So the upshot is that I get, I simulate the effect of a ground, or in other words, a lifting body approaching the ground. So what does that mean? Well, if I've got another color, my airplane is here. Now I want to look at what's the influence of this ground on the wing. And now we see that Well, this vortex here, if I drew a right angle, let's just go to the center. It's going to induce a velocity that's upward. Same with this one, a little bit upward. So the net effect is that I approach the ground. I have kind of, again, kind of like formation flight, this upward rising air. And that's been the concept behind some planes, right? At least a concept. Of course, birds do this. Some of those, just like they fly in formation, sometimes long distance birds will fly close to the ground because they can get this sort of free lift, right? This induced upwash. They can help them reduce their drag. Okay. Sometimes you got to sit and think about these things a little bit. All right. I know this is going a little bit long, but I want to just get in a few last ideas here. I'm going to skip this one for now. I'm going to jump to here. Since we talked about this already, I just want to put this together. We talked about circulation, and I said it was proportional to lift. Well, this is what that proportionality is. It's called the Kutta-Joukowski theorem. And we also said that lift is always perpendicular to velocity. Well, this occurs naturally because of this cross product. This shows me that if I know my velocity and my circulation, I can get directly the lift. And the circulation follows the right-hand rule. So in this case, my circulation, if I curl my fingers around, my thumb points in the direction of the circulation. So it's into the page right now. So if I take V cross gamma, V is this way, gamma is into the page, my thumb points in the direction of the lift. So it's always perpendicular to my velocity. And so notice that my lift is going to be directly related to that circulation that's generated, or that sort of net vorticity. One last thing real quick. You'll remember Bernoulli's equation. It has a whole bunch of assumptions, right? It's got to be steady, it's got to be inviscid, it's got to be incompressible. We got to go along a streamline. There's got to be no work or heat transfer. A bunch of those we have already in potential flow, right? It's incompressible, it's irrotational, so it's inviscid. So as long as we're also steady, which is typically going to be the case, then what happens in the irrotational flow, since we're adding one more assumption, is irrotational, is that we can apply Bernoulli's equation not just on a streamline, but everywhere, right? So for an incompressible flow, P plus 1/2 rho V squared is not just constant along a streamline, but it's constant in the whole flow field if irrotational. If irrotational plus all the other assumptions of Bernoulli's. But again, that's usually applies in potential flow. So one way this is really useful, this is the last thing I promise, is that we can simplify our pressure coefficient. So the pressure coefficient, this is the definition we've seen before. And now if I go back and I do Bernoulli's equation, let's say I start from my free stream, usually going to have a uniform flow, right? So here I've got a uniform flow coming in, and I've got some body here, and I've got some flow field around it. Actually, I shouldn't really do a blunt body. I could, just not really probably a good case for potential flow to match reality. And I want to know my pressure and velocity at some other point. Well, remember, we just said Bernoulli's equation applies everywhere now. So this is going to apply at any arbitrary point, not just along the streamline, although in this case, every streamline comes from the same reservoir that has the same quantity. So that's another way to see this is going to be the same in your rotational flow. So I'm going to solve for P minus P infinity. P minus P infinity is, what is that? It's 1/2 rho V infinity minus 1/2 rho V squared. And then I'm going to sub that in up here. And notice that this denominator is going to cancel this one. It's going to greatly simplify this one. So I get the result that Cp equals 1 minus V over V infinity squared. Okay, so as long as I can apply Bernoulli's equation, typically this is for an incompressible and of course inviscid flow, I can get my pressure coefficient directly from velocity. So the workflow is we solve Laplace's equation, it gives us phi, get the velocity field from the gradients of phi, and once I have velocity, I directly have pressures. Now that I have pressures, I can integrate, I can get my forces. Typically lift is what we might care about. Okay, that's it. It was a bit long, but we're now going to start using these things for real geometries, right? We saw that we could take these things and get like an oval or a cylinder, but now we want to see, how can I get an airfoil? How can I choose the strengths of my sources and vortices appropriately to get me any shape that I want? All right, that'll be next time. We'll start on that.